Craig, are you ready? And I'm like, yes.
Okay, so welcome to today's Earth2Earth seminar. Thank you for joining. Please visit our website, earth2earthseminar.com, for information about the series. Earth2Earth is organised by a governing board with representation from UK universities, Nature Geoscience, British Geological Survey, and any UK institution that wishes to have a representative on the board should contact us by email. It is a mission of Earth2Earth to engage the UK geosciences community with inspiring science from international leading researchers. We will do this while promoting inclusivity and diversity, supporting the advancement of early career researchers, and highlighting geoscientists' contributions to addressing global environmental challenges. Earth2Earth seminars take place every 2 weeks at this time of day. They are open to everyone, and you can join via the Zoom webinar or via the live stream to YouTube. The lecture will be recorded and with speaker permission will be available on the YouTube channel with closed captioning. Calendar links and further information are on earth2earthseminar.com. During seminars, we ask that you follow our code of conduct, which you can find on the Earth2Earth webpage. For questions, please use the Q&A channel at the bottom of your Zoom window. These may be posted at any time during the seminar, and anyone can upvote questions that they like. We will have 10 minutes at the end to relay your questions to the speakers. So today is a special Earth2Earth seminar, which was inspired by the amazing hashtag Black in Geosciences Week that we had back in September, which was a social media campaign to promote the incredible work being done by the Black geoscience community. So we are fortunate today to have Dr. Craig Poku from the University of Leeds and Naomi Rowe-Gurney from the University of Leicester. Craig Poku is an atmospheric and climate scientist based at the University of Leeds. He completed his PhD in atmospheric sciences at the University of Leeds in 2019, where he's focused on improving our understanding on fog microphysics over the UK. Craig was also one of the lead organisers for the Black in Geosciences Week. Naomi Rowe-Gurney is a planetary scientist based at the University of Leicester. She's currently in her final year of her PhD, studying the icy giants Neptune and Uranus using the Spitzer Space Telescope. They're going to speak today about atmospheres of Earth and icy planets. So first we will hear from Craig on his current work focusing on improving fog forecasting over India. And then Naomi will give us an overview of what we know about the middle atmospheres of these icy giants and how we're planning to find out more in the future. So thank you, Craig and Naomi. Craig, would you like to begin?
Thank you, Leanne. I'm just going to share my screen really quickly. Right, can everybody see this? So firstly, good afternoon, everybody. Firstly, thank you for introducing me. I am an atmospheric and climate scientist based at the University of Leeds. And in today's presentation, I'm going to be giving more general overview of the importance of fog and why aerosols are key to understanding nocturnal radiation fog. Whilst I am talking about this from the perspective of the UK, you can actually, what I'll do at the end in the discussion is I'll talk about it briefly from the perspective of India. So what's the motivation behind studying fog? Fog consists of multiple physical processes, and these processes all interact on a subtle level. So these physical processes involve a combination of thermodynamics, radiation, and microphysics. However, because this interaction is so subtle, there is actually poorly represented in models, making fog difficult to forecast. And as an example, in 2013, there was a major crash that happened in Southeast England, which resulted in 130 crashes and 12 people injured. And this was due to sudden onset fog that was not forecasted. More recent studies have been able to actually highlight the role of aerosols in fog, and the reason why aerosols are important is because they indirectly change the microphysical properties of the fog's evolution. So the point at which the fog formation happens to the point where the fog becomes really thick, aerosols are key for that transition. And so the key objective of this talk is to actually talk about what are the impacts of aerosol fog interactions during the fog evolution, and in particular, what is its role during the transition to a wild mixed layer after formation. Now, because I'm aware that a number of people aren't aware of what aerosols are, or to put it simply, when I started this work, I thought aerosols was the stuff that comes out of a link scan, I thought I'd actually give a nice schematic in terms of why aerosols are important for fog. So here we've got 3 aerosols: aerosol A, aerosol B, and aerosol C. One thing to note is that the way how fog formation happens is that the atmosphere approaches what's known as saturation. And saturation happens when the lower layers of the atmosphere begin to cool through a process known as radiative cooling. And if you have a sufficient amount of cooling that happens within the lower atmosphere, you'll then have fog. As the atmosphere begins to approach saturation, these aerosols will then allow for the condensation of water vapor to happen on them. Here we have 2 aerosols. So we've got aerosol A and aerosol B. One thing to note is that aerosol A is more soluble than aerosol B. And because even though they're both the same size, aerosol A is more soluble than aerosol B, you will find that water vapor is more likely wanted to condense on the surface of aerosol A. Now, if we look at 2 aerosols of the same solubility but of different sizes, one thing to note is that aerosol A and aerosol C have the same solubility, but aerosol A is larger in size. The energy required for you to condense on a larger aerosol is less, and so you will find that water vapor are more likely wanting to condense on the surface. And so the reason why this is important is because what you find is that aerosols that are larger in size and are more soluble are more likely to then become the nuclei of cloud droplets, which is known as aerosol activation. And this is a key bit of physics that is usually not necessarily well represented when we're actually simulating fog. So going back into how this now applies to fog, you see here that so one thing to note here is that the Earth's surface will then release heat through a process that's known as radiative cooling. If you have sufficient radiative cooling happening, you will then have saturation, and then that process of fog droplets beginning to form, as we can see with the orange dots and the blue circles will then appear. What you will then find is that through this process, some of these droplets will then begin to decrease through the atmosphere through a process called sedimentation. However, if you've got sufficient number of droplets that have actually begin to form, so going from aerosols to fog droplets, what you will then find is that these fog droplets will then emit enough long wave radiation at the top of the cloud and through these droplets to then mean that you then end up having the fog layer then form its own convection. So to kind of simplify, what you find is more droplets means more long wave radiation being emitted. The long wave radiation at the top of the cloud will be greater. This will then result in you then having an optically thick or thicker layer of fog. And so the question is, going from this formation period to a development stage, are we capturing the physics correctly, and where are the potential model discrepancies? And so for this particular piece of work, I looked at a case that is known as IOP1 from the recent local and non-local fog experiment. So the LAMFEX was a field campaign that happened in the winters of 2014 to 2016, and it was focused on trying to gain more observations to allow us to then do better model verifications to understand fog. One thing to note in this particular case, IOP1 began forming fog at 1800 UTC, and it remained stable throughout the duration of the night. So to put this into context, the initial stage of fog where we have this is what's seen as a stable layer. This is seen as an unstable layer. What you found with a number of these cases is that, apologies for that, what you found with a number of the modeling cases is that it went to that thick fog too quickly. And so my work was trying to understand why it went to that thick fog too quickly and what could we do to improve it. So to do this, I used what was known as the Met Office NERC cloud model, which is a large eddy simulation model that can resolve atmospheric flows at different scales. The simulation ran for a period of 13 hours, which was initialized with the observational data from IOP1. And because we weren't able to collect aerosol measurements for this particular case, we chose measurements that were ideal for an area such as IOP1, which was set in southeast England in an area known as Bedfordshire. Because I was mostly interested in the cloud microphysics, Monk was coupled with what was called the Cloud Aerosol Interactive Microphysics Scheme. So it's a bulk microphysics scheme that was developed to investigate aerosol cloud interactions, but the really important piece of information for this is that CASIM is being developed to be the long-term replacement for the Met Office microphysics model. And this then means that the work that I'll be developing in this particular piece of work will then actually then hopefully then result in better fog forecasts. The aerosol activation scheme in particular that I used was Abdul Razak and Gant, and I'm actually going to go into a bit more detail with regards to this later in the presentation. So what I did at the beginning of this particular piece of work is that I wanted to say, if we were to just run the model with the current model assumptions, how far off are we when it comes to actually capturing the transition to an optically thick layer? So the optically thick layer can be sort of determined by the surface visibility. So we see here that the surface visibility is relatively stable throughout the beginning of the night. And even though it does decrease during the later parts of the night, we actually find that it doesn't hit what's known as really thick fog. So it never reaches below this threshold that we see here. One thing to note is that if we run it with the control simulation, so if everything is exactly the same, we notice that this initial period of the fog formation occurs too quickly. And this is probably due to the fact that actually the way how we're representing the fog microphysics or the aerosol indirect effects is not appropriate for fog formation. However, one thing to note here is that if we look at the case where we actually reduce our aerosol number, by reducing our aerosol number, we then actually reduce the number of droplets that then form at any given time, which then means that the fog is then transitioning at a slower rate. So this is really important because what we're then actually finding is that if we then have a way to be able to have a more appropriate way to then calculate fog droplet formation so that the number is initially slower, but then it then grows in speed. So you're going from this red line to the purple line. That then means that we're then able to actually capture that transition to an optically thicker layer. And so the next part of the work that I'm going to discuss is this idea of what aerosol activation schemes can do in terms of overestimating this droplet number and what can we better do to actually improve the physical representation. So rather than me trying to explain what aerosol activation is, I'm going to use the analogy of a sink. So your atmosphere can increase in relative humidity, and once it increases in relative humidity through cooling, you then find that it will then increase in the source of supersaturation. So supersaturation occurs when there is more water vapor in the atmosphere that can be held at any given time. So imagine that you've got a kitchen sponge, you put it under the tap, and then afterwards then it's completely saturated. If you past that point, that's the source of supersaturation. But supersaturation is an unstable environment. And so what you then find is that the environment then needs to then reduce that supersaturation to then become stable. And that happens through condensation. So what you then find is that as you reach a state of supersaturation, condensation will occur, which then removes water vapor from the atmosphere. But then by removing water vapor from the atmosphere, you then decrease your relative humidity. And so the difference in supersaturation due to the increase in cooling minus the decrease in condensation, that change in supersaturation will then equate to a total droplet number for any given time. However, this assumption for a number of models is inappropriate for fog for the following reasons. The first thing is that the source of supersaturation is dependent on what's known as adiabatic ascent. So adiabatic ascent is the big fluffy clouds, i.e. cumulus clouds, that is driven by adiabatic ascent or convection. So you're basically having a physical representation of a cooling system that doesn't happen in fog. The second thing is that most aerosol activation schemes assume this minimum updraft velocity because aerosol activation schemes get used in really large scale models. And so in order for you to be able to ensure that you don't have any numerical errors, they have this minimum updraft velocity implemented. The problem is that the minimum updraft velocity, if you were to equated to a cooling rate is about 3.51 Kelvin per hour. However, radiative cooling is a much slower cooling rate, which is only around 1 Kelvin per hour. And so because you've got this discrepancy in this minimum updraft velocity, as well as the physical representation not being accounted for, you end up actually having an overestimation in aerosol activation. And so for this next piece of work, what I use the second half of this presentation to do is develop an aerosol activation scheme that could account for non-adiabatic cooling, or in this case, radiative cooling sources that are found in fog. You also may have recalled that I used a different aerosol activation scheme at the beginning of this piece, which was Abdul-Razak and Gang. We ended up moving to another scheme for the basis of this next piece of work, because the Shipway 2015 scheme is better for aerosol regimes similar to Cardington. So with the schematic that I described, so we had the change in supersaturation is equal to the increase in supersaturation due to adiabatic ascent minus the decrease in supersaturation due to condensation. This was what the previous framework for aerosol activation that I tested had. What I then did was I actually then, through a mathematical derivation, was able to also include this non-adiabatic cooling term, which we found that by including this non-adiabatic cooling term, you then found that your change in supersaturation isn't just dependent on one cooling source, or isn't just dependent on another cooling source, making it more applicable to a much wider range of cooling sources of both foggy and convective cloud regimes. And so what I'm going to show here is an example of what happens if we were to use this new particular scheme. So here what I did for the final piece of work was that I actually applied the Shipway version 2 scheme, so this dual term, into Monk. Here, we see that we've got the previous scheme. So the previous scheme here, we notice that, again, it's looking relatively stable. But the reason why we can see that it's now becoming well mixed is because we actually see that our cloud condensation nuclei and our liquid water is become more well mixed in the atmosphere. And therefore, this is developing to become too thick too fast. However, by using this new scheme, we actually find that a more appropriate cloud droplet number was being calculated in comparison to observations, meaning that by having a more appropriate cloud droplet number being calculated, you are finding that you're getting a much slower transition to a thicker fog. So you're finding that that stability point that you don't notice on graph A isn't present in graph B, therefore demonstrating the need to have a more physical representation of aerosol activation. And so in this summary slide, I'm just going to briefly touch upon some of the work that I'm now doing. So I'm now looking at fog over northern India. And what's really interesting is that the way in which visibility is calculated is usually done by the number of fog droplets. However, there's also a process that's called the aerosol optical depth, which essentially means that if you've got a sufficient number of aerosol or air pollutants within fog, within the atmosphere, that can also lead to a decrease in surface visibility. And what my work is now looking at doing is saying, okay, so if we've got a situation where we've got a highly polluted area prior to fog formation, how important is that transitional period? So if I go back a few slides. So if we've got a situation where we're having fog forming, but without saturation, how will that then potentially then have an impact on the further evolution? So the reason why I'm being a bit vague on this section is that we don't know how important that period is, but that's what my next piece of work is looking at. And so with that in mind, thank you. So thank you. Sorry for the slight chaotic bit at the end. I realized I forgot to put the slide in right at the end.
Thanks, Craig. Naomi, did you want to share your slides?
Let me just my PowerPoint's being slow today. There we go. Okay. Right, so I assume everyone can hear me and see my slides okay. So something a little bit different to what Craig just talked about. So I'm going to talk to you about the ice giants, Uranus and Neptune, and my work looking at them and their atmospheres in the mid-infrared specifically. So I'm going to give you an overview of what we know about the middle atmospheres of the ice giants, and then talk about my work using the Spitzer Space Telescope and how we're planning to find out more in the future. So because there's such a wide range of people listening today, I thought I'd start at the very beginning by answering one of the most frequently asked questions, which is what makes an ice giant an ice giant? So ice giants are smaller than the gas giants Saturn and Jupiter, but they're made of similar stuff. So they have hydrogen and helium as their base atmosphere. But the difference is they have a much higher concentration of these things called ices. And I don't just mean water ice when I say ices, it's elements that are heavier and have a higher freezing point than hydrogen and helium. So this picture in front of you is the best guess of what's inside an ice giant. So the outer cloud layers and atmosphere have methane, ammonia, water, and complex hydrocarbons. And then as you get deeper, you get higher pressures and therefore higher temperatures. So you get these other layers and things start to get a bit weird as you get deeper. So you get a supercritical water ocean, which just means hot and dense. And then as you get deeper, it gets even weirder and you get something called a solid layer of super ionic ice. And that's this hot, dense ice that has been actually made in the laboratories now. So we know this stuff does exist at the pressures needed. And then after that, so below that, you have a small rocky core. So this is just our best guess. There are even people talking about the fact that they shouldn't be called ice giants and they should actually be called rock giants. So we really know very little about these planets. So everything we do know is from our own ice giants, Uranus and Neptune, and they're both similar to each other. Because they're both ice giants, so they have similar size, they're made of similar stuff, and we think they come from the same origins. They both have ring and moon systems. They're both blue due to the high levels of methane in their atmosphere, but they also have a lot of differences. They have differences in their axial tilt, which we'll talk about, in their internal heat, in the activity of their atmospheres, and different types of satellites. So we think what we have in our solar system is something called a typical ice giant, so that's Neptune, and a unique ice giant or a weird ice giant, which is Uranus. So they're both interesting for us to study for different reasons. So let's start with our typical ice giant Neptune. So it's the furthest out planet. It takes 164 Earth years for it to orbit the sun. And the atmosphere is highly dynamic. So this video is from the only visit we've ever had to the planet. It's the flyby of Voyager 2 in 1989. We haven't been back since. And you can see the great dark spot as that big purple bruise in the atmosphere. The Hubble images on the left show how the variability of the atmosphere it's really variable over short timescales on Neptune, and we'll come back to why that's important later. So for Uranus, our weird ice giant, it's closer to us and therefore closer to the sun. It has an 84-year orbit. So it should technically be warmer than Neptune, but actually it's got the coldest atmospheric temperatures. And another weird thing about it is that it's 98 degrees, it's got a 98-degree obliquity, which means it's rotating on its side, and it's the only planet in our solar system that does that. So when Voyager 2 visited in 1986 to make this video, again, the only visit that the planet has ever had, it was at solstice, which means we can only see the pole rotating. So that's why you can only see the pole in that video. And then in 2007, as it approaches its equinox, it looks more like the top video, the rings being edge on, so then we can see the equator like we can with other planets. So we haven't been to either planet in ages, since the late 1980s. So we have to rely on remote sensing to look at them from both Earth-based and space-based telescopes. And we can do this in multiple wavelengths. Here's some examples of visible through to microwave. So all of these images here that you can see are of Uranus, but we can also apply the same thinking to Neptune. So these different wavelengths are all sensitive to different depths in the atmosphere. So on the right, that shows the vertical structure of an ice giant atmosphere, and that shows the stratosphere and the troposphere separated by that tropopause at around 0.1 bar. And we see where each of the wavelength bands sense in the different colors. So visible and the near infrared in blue and purple sense the cloud tops at the top of the troposphere. And the microwave in green senses deeper into the troposphere down to around 50 bars. And then the mid-infrared, we can see a lot more interesting stuff. So we can see the stratosphere as well as the upper troposphere, especially those photochemical hazes, which we'll talk about. And that's why the mid-infrared is so useful to us. So I'll start with some Earth ground-based observations, and they're really beautiful. There's 3 of these images are from the VLT, the Very Large Telescope in Chile, which you can see in the background image. The VLT is like an 8-meter telescope, it's huge. And then one of them is from the Keck telescope, which is a 10-meter telescope in Hawaii. And it shows how detailed we can see just from the ground. And that's even in mid-infrared. So the orange images that you can see there in the mid-infrared, and mid-infrared especially is very difficult to image from the ground because of atmospheric absorption. So between 5 and 30 microns, that's our really super interesting range for the mid-infrared. We can see the temperature and composition in that range, and we get this absorption from our own atmosphere. So we can get good spatial resolution because of these huge mirror sizes that we can get on the ground. But because of this absorption, we have poor spectral resolution. So we can only get 1 or 2 bands in these critical wavelengths. And that's why we had to go to space. So my research uses the data from the Spitzer Space Telescope, infrared spectrometer, and Spitzer is an infrared telescope that is, it was launched in 2003, the same generation as Hubble. It was decommissioned back in January of this year, on January 30th. And it was in an Earth trailing orbit, and it has a 0.85 meter collecting mirror, which is pretty small, but it's in space. So we have this uninterrupted view of the mid-infrared without having to worry about our atmosphere. And that is within those critical 5 to 30 micron ranges. So we traded in our spatial resolution for spectral resolution. So actually with our Spitzer IRS, we have 0 spatial resolution. So this is the kind of data that we get from Spitzer. No pretty images, unfortunately, like we do with ground-based, but it contains a lot of information that is really useful to us. So this is an example of Uranus data from 2007 and Neptune data from 2005. And we can see the main features, so things like the methane and these complex hydrocarbons that form these stratospheric hazes, these photochemical hazes. And they're formed by methane being pushed into the stratosphere, and then the sun breaks it down in photodissociation and creates these complex hydrocarbons like acetylene and ethane. And the overall shape of the spectrum is governed by the hydrogen-helium continuum and the overall temperature of the planet, of the atmosphere. So comparing the two, we can see a general trend. They have similar features, so they are made of the same kind of stuff. But the big difference is Uranus's temperatures are lower, like we expect to see. And these spectra are made from averaging together multiple observations at different times, and therefore at different longitudes. And that's where my research comes in. So the investigation that I'm doing is we split up these longitudes to see if anything is changing from longitude to longitude. So as the planet rotates, does it change its composition or temperature or both? And the plot on the left shows the different longitudes that the observations come from. So we have a nice range of longitudes to look at the general pattern. And so do we see a difference between these longitudes? The short answer is yes, we do. We see a consistent variation very clearly. The right plot shows the difference in radiance compared to the average for the entire range of the data. And longitude 3, which you can see in green, is dimmer consistently than longitude 4 in purple, which is brighter. So to look a little bit closer at what might be causing this difference, we've taken bands in the high and the low resolution data and found the variation for each species across those different bands that we've chosen. So the top plot shows the bands, and the bottom plot shows the contribution of each species to different pressures or altitudes in the atmosphere. So again, mark the tropopause there as that dotted line. And as an example, methane here at around 1300 wave numbers, if we bring it down and look at what depth it contributes to the stratosphere, whereas the continuum in the hydrogen helium and also something called monodeuteurated methane, which is just another form of methane, that contributes lower down into the troposphere. So if we plot these on a variation plot to see how the radiance changes over each longitude, we can see that the methane in the black points is varying quite a lot, up to 15% variation, whereas the tropospheric species that are lower down are actually very consistent. So we're seeing a change in the stratospheric species only, and this is the same for a lot of the chosen bands that we've seen. So the hydrocarbons like ethane, acetylene, they are changing a lot, whereas the tropospheric ones are staying very constant. So we know we have this longitudinal variation, but we don't know whether it's a variation in temperature or gas abundances. And we've used this thing called Nemesis, which is a retrieval algorithm that does optimal estimation retrievals to model the data. So that bottom plot shows the model versus the data that we've managed to fit it quite well. And we model each longitude in the investigation and found it was likely to be a change in temperature that we're seeing rather than in gas abundance. But it could technically be both. It's very difficult to separate those two things. They're very degenerate. So one way to find out what's actually going on, to check whether it's a temperature change or not, is to get some spatial resolution somehow to see what's going on. So luckily, this image here from the Keck telescope that I was talking about is from 4 days before this Spitzer data. So it's incredibly lucky that we've managed to find this data, especially considering it's now 2020. 2007 was a long time ago. So these images from Keck are in the near infrared, so bands H and K prime. They sense around that tropopause level that we spoke about before. And we have two hemispheres here that are centered at around 80 degrees and 230 degrees on the left and right. And we see that we have one active and one dormant hemisphere. So the hemisphere on the left has these features that are present in both bands, which means we have some kind of vertical structure in this like system, in this cloud structure. And interestingly, the meteorological activity is co-located with the coolest stratospheric emission. So it's consistent with the idea that on this active side, there's a large scale uplift that's causing a drop in temperature. So physically, this could be happening. We also have some other evidence that shows that there are other causes or places where there could be spatial variation. So this work from 2009 VLT data from my colleague Mike Roman, it shows apparent stratospheric spatial variation at 13 microns, so solidly in that mid-infrared band. And we have spatial variability being seen in multiple bands of multiple instruments at multiple epochs. So we know something could be a source of this variation. but it really is impossible to know for now. So do we see the same thing at Neptune? Strangely, we don't. We do the same exact investigation, and we see less than 2% variation across the same species. So before I mentioned that Neptune is highly variable and dynamic, so this is the opposite of what we thought would actually happen. But what we think is happening is, so in the images on the left, you can see that as it rotates, we're actually seeing no one feature that stands out because it's so noisy. The hemispheres will always look similar. So that's what we think might be happening. But again, we don't know. And we won't know until we get that spatial resolution. So the future of the ice giants is really in the James Webb Space Telescope. The other main part of my PhD is preparing for this telescope to observe Uranus and Neptune, which it's going to. It's scheduled for launch for October 31st, 2021, so Halloween next year. And it's much bigger than Spitzer. Remember, Spitzer was a 0.85 meter telescope. This one is 6.5 meters. And it's also in that critical mid-infrared wavelength range. And the ice giants are some of its primary targets, but it's also a telescope that's mostly being used to look at astrophysics and cosmological objects. So the University of Leicester is actually the mechanical systems and structural engineering lead on the MIRI instrument, which is the mid-infrared instrument in the bottom right corner. And we, as a team, have access to guaranteed time. So we are going to be observing both ice giants within the first 12 months of operation. So as I was saying, it's huge, 6.5 meters in diameter. And the sun shield is the size of a tennis court. So just a little bit of scale here that you can see that person stood next to it. So it's going to be, hopefully it will be launched next year and we'll get to see some amazing things. And because it's so big, it means we no longer have to trade our spatial resolution for spectral resolution. We can have both for the first time. So at these mid-infrared wavelengths. So we'll be able to generate spatially resolved global spectroscopic maps for the first time of the ice giants, which is really exciting. And if you look at the field of view on the left image, these are the field of views for the mid-infrared instrument for both ice giants. And it literally looks like this instrument was made for ice giant science, even though it wasn't, but it really feels like it has been. And for each image we take using something called the integrated field unit, so the IFU of this MIRI instrument, each pixel has an associated spectra. So they're called spaxels. So an example of what these spaxels will look like. So each pixel on that image of Uranus, which is a simulation of an image of Uranus taken in 2022, will have an associated spectrum. So it's a lot of information that we'll be able to use to find out the origin of this variation that we found. And this image actually is from the modeling paper that I'm working on now that follows on from the Uranus and Neptune stuff. So another thing to be excited about for the future is missions to the ice giants. We're currently in the study phase, which means that a lot of people are writing white papers and requesting money for projects, etc. And there have been a lot of gatherings to discuss the future of missions to the ice giants. So, for example, over 150 scientists from across the world met at the Royal Society in January of this year for the Ice Giants 2020 meeting. And you can follow the progress of ice giant exploration on Twitter at the Icy Giants page. So I'll leave you with a summary. I look forward to your questions, and you can also follow my Twitter in the top right for ice giant updates as well. So thank you.
Thanks very much to both Craig and Naomi. So we'd like to invite you for questions, and I've got one in the Q&A that Craig has already answered, but I'm going to ask you to answer it again and maybe give some more details. So the question is, if there's a highly polluted area before fog formation, do you think it makes the visibility even poorer because there are other PM aerosols present?
So firstly, thank you for that question. The short answer is yes. The long answer is because the surface visibility is being driven by the aerosols that are currently present within the atmosphere, what you're then finding is that the surface visibility when fog does form is being driven by your source of aerosol that haven't activated into fog droplets in conjunction with the fog droplets that are also then emitting to the decrease in surface visibility. And so essentially you've got this combined coupled effect, which then means that if you, for example, and for context, I went to Delhi earlier this year. When we landed, there was a really thick fog. You couldn't see the person in front of you. And that is due to the fact that you've got both the combinations of these PM 2.5, these pollutants, as well as these fog droplets that are all activated.
And a kind of follow-on question from that, which is a question of mine, which I hope is okay. What are the other potential factors you think that might be driving the fog formation that perhaps haven't been taken into account before? Are there likely to be different factors to affecting fog formation elsewhere?
So for context, in the UK, I looked mostly at rural fog. So that then meant that you kind of remove a lot of the factors that can potentially prohibit fog, such as urban heat islands and other like really big sources of pollution. But in Delhi, what makes it quite interesting is that because the case study I'm looking at is over Delhi airport, what you're finding is that factors such as heat release from buildings and surface types, as well as also the sort of like dynamical winds directions around the actual buildings themselves, they can all have impacts on fog. And what you find is that with urbanization, increases in urbanization can either prohibit or enhance fog depending on which city it is. And the reason I say that is because we don't know at what point does the aerosols become more important over the changes in urbanization. So that's changes in, say, heat release, and which one should take priority depending on it, because the reality is that fog is still a very difficult thing to study.
I've got a question for Naomi. What's driving the tropospheric activity on Uranus?
Oh, that's a good question. So Uranus is weird because it has this negligible internal heat source. So we're not sure even whether it has a negligible internal heat or whether we just can't see its internal heat due to some kind of process that's blocking that internal heat from our observations. So it really is a complete unknown as to what is going on as a in terms of the processes, both chemical and dynamical, in at the depths that I was talking about. So everything that we look at, we are kind of doing our best guess at the moment. Without James Webb Space Telescope and some kind of probe, it's really proof. It's difficult to make any kind of assumption.
A sort of, I guess, follow-on question from that, which we've also had, which might also be difficult to answer, but is it likely to be the same process on Neptune but just less active, or is there just no way of telling at this point?
There really is no way of telling. I mean, we think that the lack of activity on, or the apparent lack of activity on Uranus is because of its lack of internal heat source. And Neptune obviously has this much more active atmosphere due to all the energy coming from its heat source. But again, it could just be that we're not seeing the full picture, that something's blocked, and who knows, honestly.
I've got a question for Craig. What role does fog have on the overall radiation balance of the atmosphere? Does it drive net cooling or heating? And do we know how more or less foggy the world is now compared to pre-industrial periods?
Firstly,
thank
you for that question, Oliver. I was reading it about 4 times just to understand what you were trying to say. The short answer is we don't know. So in terms of fog's impact on climate, or the change in foggy conditions due to climate, that's an area that is still hasn't really been investigated. But the one thing, and the reason why I also say I don't know, is because different aerosols, depending on the properties, the chemical properties, can either absorb or scatter solar radiation into the atmosphere, which then will result in either having a net heating or a net cooling. If you change that net heating or net cooling balance, you then will change the initial atmospheric profile, which will then change the timing in which fog formation will occur. So because of that, it makes it very difficult to then decouple the impact of aerosols versus the impact of aerosols in conjunction with fog. I do suspect that the number of fog cases probably did increase from the pre-industrial to the industrial period. But then what you'll then find is that there's also, so this is answering your second question, but then there is a thing that's known as the boomerang effect. So if you increase the number of aerosol in any given space, you then also increase the number of aerosol that can then activate into fog droplets. So there you have more droplets, and then you have more long wave cooling being emitted at the top of the layer. If you then have enough aerosol that the water vapor is then at too great of a competition such that they can't then form fog droplets, you then actually can then suppress the number of droplets will then begin to form. And so essentially you have what's this boomerang effect where you have increase, point, and then decrease. Because nobody's really looked into this problem, I couldn't tell you the answer, but I suspect that it probably had an increase and there was a sudden decrease. I hope I answered your question, because I don't even know the answer myself.
No, that's great.
I'll unmute myself. You'd think by now I would know to check if I was muted. Question for Naomi. You use the terminology troposphere and stratosphere with the tropopause at 0.1 bar, which is an identical pressure to those on Earth. Are there similar physical analogues in the ice giants, e.g. convection in the troposphere, temperature inversion in stratosphere, or are they mostly descriptive terms? Is there something general about 0.1 bar?
Yep, so it's the same as on Earth. You get a temperature inversion at that point. It's minimum temperature is at that tropopause level. Yeah, that's pretty much it.
Okay. Do we have any final questions or comments for either of the speakers? I'll just give it a minute in case any will come through. While we're waiting, I did have a question about the mission. So it will be launched October 2021. Is there any indication of when you'll start getting data back in a kind of way that can be processed?
So it's launched, and then it should take about a month to get to its point, slow down, make sure it's all cooled down, and then all the calibration stuff starts. So it should be around January 2022 that data starts coming back that can be used, I think. But there are quite a few windows as to when the ice giant observations can happen. So it probably like late 2022 or summer 2022, hopefully.
Okay, thank you. So I will start to wrap up now. So thanks again to Craig and Naomi for your talks. They were really, really interesting, and thanks for sharing your research with us. And thanks to everyone who's attending via Zoom and YouTube as well. Please check out our webpage and our Twitter page for details on upcoming seminars. And our final event before the Christmas break is 2 weeks from today at 3 o'clock. And Professor Josh West from the University of Southern Carolina will be talking about chemical processes that occur at the Earth's surface. So thanks very much, everyone, and hopefully see you in 2 weeks. Bye.